Okay, that's recording. Oh shoot! Since I'm using my phone for that, I need. Hopefully, I brought my iPad. Let's see though. When did he move? I would guess he had 3 years from when he left. So I guess he did a good amount of his general ed at MCC, but still had to do some at the U. So that's 1 year, and then 2 years for the actual stuff specific to computer science. But then hopefully he goes on and does like a master's.
I'm pretty sure he said he's going to graduate next semester. When he was talking to Jessica. He left up last winter. Last fall, actually. So, he's been there for 4 whole semesters.
So 2 years. So yeah, I would guess he has 2 more semesters.
Oh.
Okay.
What is that? Fall or winter semester? 20.
Fall semester 2018.
Summer, fall, winter, spring.
Spring and fall.
He's in spring. Oh, spring.
So let's think for a second about functions. Now, the simplest type of function that we can think about would be of the form f of x is equal to f of x naught plus m times x minus x naught. Which is just the equation of some line.
Okay.
Y equals mx.
You said this is the easiest way to think of an equation.
Not the, well, you're used to thinking about y equals mx plus b, right?
Mm-hmm.
Where b is the y-intercept.
Mm-hmm.
So, if b is the y-intercept, then this is the same thing. Let's, instead of y, let's do f of x, you're good with that.
Yeah.
And instead of plus b, we would say plus f of 0. That's the same thing as y-intercept. What's y when you plug in 0? Right? And so, to write it in this form, now what do you have? You have f of x is equal to f of 0 plus m times x minus 0. But this is just a line that goes through the point x naught f of x naught. It's a line that goes through the coordinate x naught f of x naught. So it's a line containing that point. Is that weird to you already?
No, that means
I'm wondering how x turns into x minus x naught.
How x turns into x minus x naught.
x minus
Okay.
0.
Let's think about it this way for a second. Let's say we got some line f of x is the graph of that function. And we'll say that this is some point x naught that we know is on f of x. Okay? So what do we know? We know that, well, so then we know the value of the function at this point. So over here, this is f of x naught, right?
Okay?
Because it's the height at that point,
Yeah.
right? So now, thinking about it, how's the right way to say this? So now let's think about the line that goes to that point with a slope of m. Does that make sense? Or you can think about it with 2 points. How do you find a line given 2 points? I still don't. Here, let's say it this way. Pick any other arbitrary point on here, x. Maybe this one.
I'm confused to what we're trying to do.
Right now I'm just saying, look, this is the equation of a line that goes through a point.
Okay.
Maybe instead of trying what I was thinking, seeing an example.
Yeah.
let's say that f of x is equal to
3x plus b.
2 plus 1/2 x minus 2. What am I saying? I'm saying that this is a function with a slope of 1/2 that goes to the point 2, 2.
Mm-hmm.
Right? So let's just graph it real quick and see this in action. When you plug in, and maybe for the sake of plugging in, writing this out real quick, a little simplified. So I'm going to do 1/2 x plus 1. You good with that?
Mm-hmm.
Okay. So now we can just pick values and see what we get. When we plug in 0, what do we get?
You get 1. Or 3.
You get 2.
When I plug in 0,
You get one.
what do I get? 1.
Yeah, but what happened to your 2 right there?
2 plus 1/2 times negative 2 is?
Oh.
Good?
Yeah.
So that's my simplification. Okay. And now when I plug in 2, what do I get?
You get 2.
2.
Okay.
So it goes through 2, 2. Oh. 2. When I plug in 2, I get 2. Oh, I did that one. When I plug in 2, I get 2. There we go, sorry. So I know that the function goes through 0, 1, and I know it goes through 2, 2.
Okay.
So what's the slope of it?
1/2.
1/2. Okay, so there we go. That's a line that goes through those 2 points. Therefore, it contains this point, like we said, and has a slope of 1/2. So this is an equation of a line that goes through x naught, f of x naught. And has a slope m.
Okay.
Okay? So the idea with the derivative is we want to find the tangent line at a particular point. So I want, you know what tangent line is?
Mm-hmm.
It intersects our curve at a single point. So if I have a curve that looks like this, and I say, what's the tangent line at this point? It's the line that goes through only that point.
Okay.
Seems impossible.
That's what tangent line is. And so we'll give a rigorous definition of what exactly we mean by that. But in other words, what's the slope of a function at a point? That's what the derivative is meant to capture, the slope. The two big ideas in calculus after continuity is differentiation and integration. Differentiation, the idea is to give you the slope of a function at each point, and then the idea of integration is to give you the area under a curve.
Okay.
Okay? So when I have a function that's just a line, what's the slope of it going to be? Just whatever the slope is. It's just always going to be n.
Mm-hmm.
So nothing interesting here. So now, that's all we were trying to get to. That took way too long to say. But what about for some arbitrary function? What about if I have some function that's some curve that goes like this? Here's f of x. And we'll say that this is the point x naught. And then here's f of x naught. What's the slope of the function at this point?
The derivative.
Well, we don't know what a derivative is yet. How do we get the slope at that point?
I don't know.
We don't know how, but how might we get close?
You get
Line
super
2
close
points.
points, yeah.
Yeah, you need 2 points, right? So we pick a point close, x, I know this isn't really that close, but close enough, x, and then the coordinate at this point is going to be f of x, right? So this is x comma f of x, and this point over here, instead of doing these labels, I'm going to do it just like this. This is x naught, f of x naught, right? So that gives us this triangle. What's this distance?
X.
X
Or-
minus x naught.
Yeah.
X minus x naught. And what's this distance? F of x minus f of x naught. Right?
Uh-huh.
And so our slope is going to be approximately f of x minus f of x naught over x minus x naught. Rise over run.
So much deja vu, dude.
Yeah, seriously.
Okay.
So the whole idea behind it is, as I make my x get closer and closer and closer to x naught, this slope is going to get closer and closer to the slope of the tangent line that goes through just that point. That's the big idea. Okay.
The coolest concept ever.
So now let's just get straight to definitions and start actually doing some of this stuff rigorously. But that's the idea. We're going to come up with a function that gives us the slope of a tangent line at each point in another function.
Oh, and they're all going to be separate tangent lines?
It's going to say, so I'm going to come up with a new function, call it f prime of x. And what's going to happen is when you give it a number like 2, then it's going to give you the slope of the tangent line at 2. And the slope of the tangent line at 2, what is that?
The function
Roughly
is gonna
1/3.
give you that.
Yeah, the
Yeah.
function is going to give you the slope. That's what we call a derivative. So you have a function, its derivative is a different function that gives you the slope at any point of your first function.
Okay.
Does that make sense?
Mm-hmm.
So in other words, this is going to give us roughly, each time, f of x minus f of x naught, if you plug in x naught here, over x minus x naught, where this x gets really close to x naught. It's going to roughly give you that.
So we're picking the x.
X naught.
We're picking the x naught.
Yeah, so you pick 2. Then I'm going to pick a point x really close to 2 and give you the slope. That's what this function is going to do, this f prime function.
Okay.
When we already have some different function f of x. So we define f prime in terms of f. So f's this curve, then my f prime gives me the slope that a tangent line would have at that point. Or we roughly say the slope at the point, or yeah, I think that's pretty much what they say. So that's what we mean when we say the derivative function, the derivative gives you the slope. Okay, so now let's give an actual definition. So first we'll do differentiable and then we'll talk about the derivative function. And the idea is we're going to take the limit as x goes to x naught of the sink. And that's going to give me it exactly.
We can give you what exactly?
The slope.
Oh.
The slope of that tangent line.
Because the tangent line.
is the tangent line is the what we're approaching, right?
Well, the
Because
tangent line is going to get smaller,
tangent-
smaller. Okay.
Not smaller.
The
If
tangent
I have a
line
curve,
stays the same.
Pick a point.
X.
Some point. X naught. There it is. Okay, there's f of x naught.
Mm-hmm.
There's a tangent line to this curve that goes through that.
Yeah.
What's the slope of that tangent line?
I don't know.
That is going to be, here's what we're going to find out it is. So the slope, we use a prime, we're talking about slope at x naught, is equal to the limit as x goes to x naught of f of x minus f of x naught over x minus x naught.
Are we perfect?
It's going to be a definition.
How do you do that? Oh yeah, because we just
We don't, this is intuition for what tangent line is. We're going to have to come up with a definition for what tangent line is. And it's going to be this. But what's happening here? So,
What is happening?
Right.
let me redraw a picture of the course space. Let's do this one more time and see what's happening.
I
And
have
then
a
we'll
really cool
do our
picture.
definitions.
Who?
So, here it is. We've got
Oh, yeah.
some curve.
Weird. Yeah.
Some random curve. And we want to know the slope here at x naught, right?
Okay.
So what are we going to do? We're going to take some point, x over here, and that goes to f of x right here. So what's coordinates of this point? This point is x naught, f of x naught.
Mm-hmm.
And the coordinates of this point are x, f of x. Now, the slope between these 2 points is rise over run.
Mm-hmm.
So the slope at m naught, I'll do m naught for the slope at x naught, is going to be roughly the rise minus the run.
Okay, now where's your tangent line?
My tangent line is right here. So there's my tangent line.
So does it have to go through both points?
No, it only goes through one. We're making, so I'll do my tangent line in red. So my tangent line is this point. Here's this line, right? There's my tangent line, roughly. When we do this calculation, we're going to get the slope to this line, which is not the tangent line, right?
Yeah.
But
As you pull that X.
as I take the limit of this, as x approaches x naught,
Oh,
as this point gets closer and closer to this point, this line gets closer and closer to coinciding with the tangent line, right?
oh.
And so once it coincides, oh, then we have our slope. That's the big idea. Okay. So now let's write the definition more. Let I be a neighborhood. Oh, did we define a neighborhood?
No.
No, it comes after. So it comes right after it. For a number x naught, an open interval I, a to b, that contains x naught is called a neighborhood of x. Oh.
Definition. If x naught is in an open interval AB, then AB is that right? Let's see. An open interval I equal to AB that contains x naught is called a neighborhood of x naught. Yeah, that's right. So it is a neighborhood of x naught. So an open interval containing a point is called a neighborhood of that point. Just terminology. Okay. Now let's go to our next definition. Huh?
You thought of the word neighborhood. Why does that say name?
No, I'm more wondering like, all of a sudden we're doing neighborhoods here.
It's just, the idea is they're close to the x naught. Those are the points close to it. They're in the same neighborhood. Let I be a neighborhood of x naught, then f from I to R is differentiable at x naught provided that the limit as x goes to x naught of f of x minus f of x naught over x minus x naught exists. We call it f prime of x naught, whatever that limit is. And we call it the derivative. We call this thing, whatever the limit of this thing is, the derivative of f at x naught. Okay?
Of f at x naught.
Yes. So, we have a function from a neighborhood to the real numbers. We say it's differentiable at x naught if this limit exists.
Okay, so the limit is called the derivative.
And if this limit exists, this limit is called the derivative of f at x naught. And we denote it this way. This is shorthand for this derivative because we do it so much.
So if the limit is going to equal the slope of the tangent line, then the tangent line, the slope of the tangent line is the derivative?
Sure, we don't, that was just intuition. We're going to define a tangent line later. But yeah. So now we're getting back to just rigor. No pictures of I mean, we know this is meant to capture a slope, right?
Uh-huh.
But just everything else aside, all the intuition aside, just the exact definition. What are we saying? We're saying if I can take this limit on a function, if it's possible to take this limit, at this point x naught. If that's possible, then this function is differentiable at the point x naught, and we call it the derivative of f at x naught.
Differentiable.
Yeah, so instead of a function being continuous at a point, look, we have the idea of a function is continuous at a point if something, right? Now we're saying this function f is differentiable at a point x naught.
Differentiable, what does that mean?
What did it mean to be continuous?
And that it converges to.
What did it mean to converge?
X minus x naught is less than epsilon.
The point is we're making a definition. What does differentiable mean? It means that this limit has a value. Or intuitively it means we can calculate the slope at that point. So for example, if our function looks something like this, and we're talking about that point, you can't find a slope at that point. Because there's not one tangent line to that point. That's tangent line, that's tangent line, that's tangent line, that's tangent line, that's tangent line. There's intuition. But here's what we're saying explicitly. So the same way that we said a function f is continuous at x naught if something, right? We're saying that a function f is differentiable at x naught. What does differentiable mean? I'm telling you right now. It is differentiable, whatever that word means, at x naught if this limit exists. If it's possible to take this limit, if when you do this you get a number, okay, that's something you can do. Doesn't matter what the number is. If you can do this and get a number, then it's differentiable at x naught. Okay? Now we have more ways of saying that. Instead of saying that now we have ways to talk about what this number is.
A derivative.
Yeah, we call this number the derivative of f at x naught, and we denote it like this.
Okay.
So differentiable at x naught means we were able to find its derivative at x naught.
Okay.
Does that all come together?
Yeah.
Okay. So there's our definition for differentiable at a point. Okay. Definition. If the function f from I, where I still an interval, to R is differentiable at every point in I, comma, we call the function f prime from I to R the derivative of f.
Right.
So the derivative is the whole function. You can do the derivative at a point, which is where you plug a point into the derivative function, or you can think about just the derivative function.
For all of our proofs, are we going to have to use this interval, this neighborhood?
We'll see examples of how to do something. All right. Another definition for tangent line now. If f from I to R is differentiable at x naught, then y equal to f of x naught plus f prime x is the tangent line of f at x naught. And remember what this is. This is just a line that goes through this point, x naught, f of x naught. Remember, f prime of x naught now is the slope. So this gives us a slope.
Oh, that's your m.
That's your m. So the slope of the tangent line is the derivative of f at that point, which is what we wanted.
Okay.
So now we have a definition of a tangent line. Make sense? So from here on out, when I'm talking about tangent line, you already had intuition for what it was. Now we can say it's this exact thing. But notice, a tangent line only makes sense on a function if it's differentiable at that point.
Wait a minute. What's going to be your x naught on a tangent line? What's going to be your y-intercept on a tangent line?
So should we just do a quick example?
Or does it matter?
I don't understand the question, which is what I'm just going to do.
Actually, I actually understand what I'm really confused about.
What are you really confused about?
Or what I just cleared up in my head. We're dealing with an actual line. We're not dealing with a point.
Okay, so let's really quick find the derivative then of a simple function. Proof. Let's say, given f of x equal to mx plus b, which is a line, right? Maybe not given, we'll say if. If f of x equals that, then what's our slope going to be anywhere on that?
A derivative function.
What is the slope of this thing?
M.
M. So then I want to prove that our slope anywhere is m. Our derivative anywhere is m. The derivative function is just m. That's all it is.
Oh, this is a straight line.
It just gives you the slope at a point. It doesn't matter what point you're talking about, the slope's always m.
Right.
So it shouldn't matter what point you're talking about, the slope better always be m.
Okay.
So let's prove it. Okay, so how do we do it? We need to prove that, well, we need to differentiate the function like this. We need to take the derivative, right?
Mm-hmm.
Okay, so let's do observe that the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. I probably should have started out with let x naught in R.
Okay.
Right?
Yeah.
We need to pick some random number R in R, and we need to show that it's differentiable at that point, and furthermore, that the derivative at that point is m. So pick any point you want, the derivative at that point.
Have you found on the function?
We've done this a lot of times. If I don't know anything about x naught, if I just know it's a point in R, then it works for every point in R. It works for every point that satisfies a property is in R. So one should have been let x naught in R. 2. And observe this. Okay. What's this equal to? This is equal to the limit as x goes to x naught of, plug it in. What is f of x?
Mx plus b.
That's mx plus b minus f of x naught. So that's going to be minus m of x naught minus b over x minus x naught. Any questions in what I've done so far? Just plugging in the value of the function. You good?
Mm-hmm.
Okay, the b's go out and we can factor out an n. So that's going to be m times the limit as x goes to x naught of, what's in the numerator?
X minus x naught.
X minus x naught. What's in the denominator?
X minus x naught.
X minus x naught, which is equal to m times the limit of 1. Just like that. Which is equal to n. Okay, that's what we're trying to prove.
How can you take that n out?
It's
not
constant.
in the denominator.
It's a constant. I just factored it out. If it's not in the denominator,
Sorry, I was confused, but I understand now.
you understand that? Okay.
Easy peas.
There we go. We just proved that the derivative of this is m, just constant. Now, sometimes it helps to see a graphing of both of them so that you understand what we just did.
Let's do that.
So, now when you do a graph, you have to pick a particular function.
So let's do 2x plus 1
2x plus 1/2.
half.
Okay.
Yeah.
So if we were to do f of x equals 2x plus 1/2, then we know that f prime of x is equal to what?
1 half.
Just 1/2, right? Oh, 2. 1/2, that's an
Oh yeah. I am stupid. So.
F of x equals.
If f of x equals 2x plus 1/2, then f prime of x is just equal to 2,
Yeah.
right? So let's graph both these things to see what's happening. Alright, so that goes through the point 0, 1/2, and then for every one we go over, we go up 2, right?
Mm-hmm.
Like that. So you're going to have to suffer through my artwork, but roughly like that.
A meter square.
And then, what does the graph of this thing look like? It just looks like this. So this is the slope at this point. This is the slope at this point. This is the slope at this point.
Hold on.
Pick a point.
1.
1. Okay, 1's right here. What's the slope at 1? Look at the slope function. Oh, it's 2.
But it's not on that line.
Pick another point. Let's do a point over. 1, 2, 3. At 3, here's the value of the function at 3, right? Here's the value of the function at 3. What's the slope at 3? Look down at 3. Oh, it's 2. Look. F prime at 3 gives me the slope at 3, right?
F prime at 3. Okay.
F prime at 3 gives me the slope at 3. Does that make sense?
Not really.
That's what F prime is. Right?
F prime is that right there.
It's this thing,
Okay.
which is giving me the rise over the run, taking the limit. So it gives me the slope.
Okay.
So that's what we said here. We said the tangent line at a point x naught is the line y equals to some point times, here's your m, slope. Remember, this was rewriting this function. F of x is equal to f of x naught plus m x minus x naught, right? Here is a line with slope m that goes through this point, x naught, f of x naught. Here is a line with slope m, or f prime of x naught, that goes through this point. So, we were saying if f of x equals mx plus b is a line, then its derivative is always just going to be m, the slope. You with me on that?
Yeah.
So what is the slope of this function at 2? If I plug 2 into this function, what's the slope going to be?
N2 plus b.
It's still just m. M is the slope everywhere.
Yeah.
If I draw this line, what's the slope of the function here?
That line.
It's still m, right? What's the slope of it here?
M.
What's the slope of it here?
M.
So the slope of it everywhere is just m. So if the slope of it everywhere is just m, then our slope function better be just m, which is what we were proving, right?
But now,
So let's go about this the other way. Here, we'll reverse engineer this thing, and I think that this will make sense. So first I'm going to draw a function. Give me a line to plot.
5x plus 2.
No, we'll start with steep slope. We'll do y equals 3x minus 1. How's that? Okay, so let's draw this line real quick.
Okay.
Or better yet, do say f of x equals that. F of x equals that, right? So let's plot this real quick. You got -1, you got 1, 2, you've got 2, 5, and whatever. It continues roughly the same pattern after that, right? whatever it does. Slope of 3, right? So now, in red, I'm going to plot the slope of this thing. Let's see, what was the slope at this point?
3.
So at this point, I'm going to draw a point for 3. What was the slope at this point right here?
It's 3.
It's 3, so I'm going to plot, okay, it was 3 at that point. What was the slope here? Oh, it was also 3. What was the slope here? Oh, it was also 3. What's the slope everywhere? 3, 3, 3, 3, 3, 3, 3, 3. So that means my f prime of x had better equal 3.
Okay.
So let's check that real quick. We'll use this, let's see what f prime of x is. So we're going to take the limit as x goes to x naught of f of x minus f of x naught, right? X minus x naught. Now we're doing it at 3. Or sorry, not at 3. We're just showing what this is in general. Okay, so let's see what that equals to. That is equal to the limit again. We won't bother writing the limit over and over again. What is f of x?
3.
3x minus 1. What's f of x prime? That's 3x prime minus 1, but that's going to be minus 3x naught plus 1, right?
Okay.
That's f of x minus f of x naught over x minus x naught. Remember, we're still taking a limit. That's equal to the limit of negative 1 plus 1 is 0. I'm going to factor out the 3.
Okay.
So that's it. I'm going to plot the 3 all the way out of the limit. You good with that? 3 times the limit of what's in the numerator?
X minus X naught.
X minus X naught.
What's in the denominator?
X minus X naught.
Which is equal to 3, because this is just 1. Oh, look at that. F prime at any point you pick x is always just 3.
What if X naught is bigger than X?
It
Doesn't matter.
As x approaches x naught.
If x naught's bigger than x, then this is a negative number, right? And this is a negative. And negative divided by negative is a positive. So we're back to 1.
Yeah.
So this is 1 no matter what. Make sense?
Yeah.
So that's what it's capturing. Okay. Hopefully that illustration was helpful. So let's do some more proofs. Let's prove that, or let's find the derivative of f of x equals x squared. So this one's a bit more interesting. Because now the slope changes on x squared. So maybe do a picture and then try to like guesstimate what's going to happen, and then we'll do it legitimately. So 1, 2, 3, 4, 5. Okay, so now let's look at the function f of x equals x squared. We're going to find its derivative function, right?
Okay.
Okay, so first off, let's graph this thing. At 0, I get 0. At 1, I get.
1.
At negative 1, I get.
1.
At 2, I get.
4.
At negative 2, I get.
4.
And we won't bother anymore with it, but we know it's going to look very roughly like this, right?
Okay.
So what do we see the slope doing? We see the slope over here.
Super steep.
So starting out in the middle, what's the slope at the bottom?
0. 0.
0, right? So it's going 0 and it's getting bigger and bigger and bigger and bigger and bigger.
Really fast.
Or it's getting more and more negative, 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 negative. Right? So I know that my function, my derivative now, the red one, I know that over here it's going to be down here. It's negative over here, it's 0 here, and it's positive over here.
Okay.
But what this looks like exactly, I don't know. It might be some weird curve that comes up like that. But we at the very least expect it to be negative numbers over here, 0 over here, positive over here. And we expect it over here to get bigger and bigger, and over here to get smaller and
Oh
smaller.
my word.
Okay. Bad with this.
Does that make sense? What we expect? Because the slope right here is a really big negative number. It's going down fast. Over here, it's going down, kind of like a 1. Over here, it's going down really slow. Over here, it's not going down or up at all. The slope's 0. And then the slope starts getting bigger and bigger and bigger. Right? So we expect it to have some of those properties, but it better go off towards infinity up here, and it better go off towards negative infinity down here. Because that gets more and more negative slope, and that gets more and more positively sloped, right? So there's a little bit of information that our intuition should give us about this thing. Now let's find it. So we are finding the limit as x approaches x naught of f of x minus f of x naught over x minus x naught, right? Okay. This is what f prime of x is going to equal. Okay, so plug in our function. This is going to be the limit as x goes to x naught of x squared minus x naught squared over x minus x naught. Right?
Okay.
Because f of x is this function.
Factor it out.
Okay, that's a difference of squares. We can factor that. This is equal to the limit as x goes to x naught of x minus x naught, x plus x naught, all over x minus x naught.
Okay.
Okay? Remember, when we're doing the limit as x goes to x naught, x is never actually equal to x naught. It just gets closer and closer. So this is never 0.
Okay.
So we're never dividing by 0. So we can cancel this out with this. So it's equal to the limit as x goes to x naught of x plus x naught, which is equal to x naught.
Okay. X gets close to x naught.
Right? The limit of x as x goes to x naught is just x naught. The limit of x naught as x goes to x naught is just x naught. Add them together. Good? Okay, so what did we just find? We just really found that f prime at x naught is equal to x naught. Right?
Right, now we got to do this one.
So, what does that mean? That means for any x you plug in here, the slope is just 2x. Because x naught can be any number. So, you good with this? F prime of x is equal to 2x. Now let's graph that. What does that look like?
What? Should have looked like that.
Let's graph this thing in red. Plug in 0, what do you get? 0. Plug in 1, what do you get?
2.
2. Plug in 2, what do you get?
4.
4. Plug in negative 1, what do you get?
Negative 2.
Plug in negative 2, what do you get?
Negative 4.
Negative 4. It's just this line, right? You're going to do this bad, but something like that. But that's exactly kind of what we expected, right? The slope is getting bigger and bigger and bigger here. The slope's getting smaller and smaller here. It's 0 here. The only thing that we might not have expected is the slope is changing at a constant rate.
Right.
So the slope here is always 2 bigger than it was here, is always 2 bigger than it was here, is always 2 bigger than it was here. So the slope is incrementing by 2.
That is so cool.
So there you go. There's more intuition for this derivative capturing the slope. Are these pictures really helping cement it in, or is it?
It's helping cement it way more unique, for sure.
Okay.
It's making much more sense.
So let's really quick show where you can't take, where a function isn't differentiable.
It's going to be the absolute value function.
Yep, it's going to be the absolute value function.
I
So
remember that because I'm so good.
prove f of x equal to the absolute value of x is not differentiable
At 0.
at 0. Okay? Now we can do this with sequences, or we can do it with the limit as x goes to x naught. Doesn't matter how you want to do it. But
What do you mean sequences?
if you don't like thinking about it as a limit as x goes to x naught, we can always pick an xn that converges to 0 and do this with xn.
I like X naught.
So if we take the limit as x goes to x naught, and we require that we're only going to use positive terms. So there is a sequence that converges to, sorry, not x naught, but 0 now. There is a sequence that converges to 0, that's always positive terms, like 1 over n, right? So remember, if we're proving it's not differentiable, all we need to do is find two sequences that give us different limits, and we're done.
Okay, now I need to get.
Yeah, so
Why does
Sorry.
sequences when you get
So a function is differentiable at x naught if and only if the limit as x goes to x naught exists. This limit, right? With me so far?
Yeah.
and you show them that?
How do we show that this limit doesn't exist? We show if we pick one sequence, if we pick one way of looking at it, we get one number. If we pick another way of looking at it, we get different
That's
numbers.
how we show it start
Oh.
converging.
No.
A limit is a type of convergence,
Oh yeah, sorry.
right?
Yeah.
You can't converge to two things. You can't evaluate a limit and get two different numbers out of it,
Oh.
Yes.
Yeah.
right? So, if I restrict myself to just positive numbers, which we know that we can find a sequence where that works, right? Where x is just positive terms, like 1 over n. Then, the limit of f of x minus f of 0 over x minus 0 is equal to absolute value of x minus absolute value of 0 over x minus 0 is equal to, sorry, I need to keep doing my limits, but I'm not getting it.
Oh, that's 0.
What's the absolute value of x? If we require x is greater than 0,
Just x.
it's just x. And I won't bother with the zeros anymore. Which is equal to 1, right? Okay. So we got the limit when we restrict ourselves to positive numbers was 1. The limit as x goes to 0, if we restrict ourselves to negative numbers, which we can do, right? Like negative 1 over n converges to 0, and that's all negative numbers. Of f of x minus f of 0 over x minus 0, this is just equal to the limit of absolute value of x over x. You do it, we skip into that instead of putting the zeros in.
Yeah.
Negative
Which is equal to the limit of, what's the absolute value of x? Negative x, since x is negative.
Okay, so big picture again. What were we thinking?
We're showing
you
that-
can't have two different limits.
If a limit exists, then it's a number. It's not two numbers, it's a number. A limit is a number.
Right.
1 and negative 1 is not a number, it's two numbers.
Right.
I mean, ultimately, what does the limit of this mean? It means every sequence x that converges to x naught but doesn't include x naught, then when you take whatever you're doing with that sequence, it comes to a number. So if I can find two sequences, or two ways of coming to x naught, that give me different numbers, then the limit doesn't exist.
Right.
Right? It's like if I plug in one sequence and I say, oh, when I plug in one sequence, I got the limit is 1. And when I plug in another sequence, I got the limit is negative 1.
Right.
Then it wouldn't be continuous, for example, right? Okay, anyway, so we get, if we restrict ourselves one way, we get a 1. If we restrict ourselves another way, we get negative 1.
Oh wait.
A limit can't be two numbers.
Wouldn't x be? Wouldn't the denominator be negative x as well because x is less than 0?
No, x is still just x. It just happens to be a negative number. Positive over negative. This is the one that's positive. Negative x is positive.
Right.
Good? Okay. Alright, let's do some more proofs. What's next? Prove. Okay, x to the n. I won't write this as a proof, but you could write it as a proof. I'm just going to find the limit exactly. So now let's find, well, let's view it this way. If f of x is equal to x to some natural number, what does f prime of x equal? And we're going to show it equals n times x to the n minus 1. That's what we're going to prove. If f of x equals this, then its derivative equals this. That's what we're proving, okay? Alright, so let's do it. So we're taking the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. And x naught is just some number in R. It's any number in R. Pick any number in R, and then we'll start evaluating this. With me?
Okay.
So in this case, we're going to get that this is going to equal n times x naught to the n minus 1. That's what we worked out. That's all said that. Does that make sense? Huh?
We don't have any n.
Yeah, we do.
Is that just some constant?
It's just the natural number. So x naught is just some number in R. Maybe I'll say it this way. Then f at x naught is equal to x naught to the n minus 1. That gives us our x naught. Okay, anyways. So here's what we're doing. Now plug in our function. So this is the limit as x approaches x naught of x to the n minus x naught to the n all over x minus x naught, right? Now this is exactly that theorem I told you again that we're going to use.
Squares.
Not squares. I have a difference of two things to the same power.
Yeah.
I can factor out one of them, and then I'll show you what leaves behind, but here's what this essentially equals. We have x minus x naught times x to the n minus 1 plus, well, maybe I'll write it out explicitly so you can see the formula happening, plus x to the n minus 2, x naught to the 1, plus dot dot dot, plus x to the 2, well, we'll go to the 1, x naught to the n minus 2, plus x to the 0, x naught to the n minus 1. Are you all good with what that numerator says?
Yes.
You good with that factoring? Okay, lovely. Now, x minus x naught and x minus x naught cancel. So this is equal to the limit as x approaches x naught of just this thing. Of x to the n minus 1, x naught, I'm not going to do the 1s to 0 anymore, plus x to the n minus 2, x naught, plus dot dot dot, plus x times x naught to the n minus 2, plus x naught to the n minus 1. Okay, you good with that?
Yeah.
Okay, now I'm just going to take my limit. The limit, so think about this term. What's the limit of x to the n minus 1 as x goes to x naught?
X naught to.
It's just x naught to the n minus 1, right?
Yeah.
So taking the limit, we're going to get, this one is x naught to the n minus 1. This one is x naught to the n minus 1.
Yeah.
This one is
X naught to the n minus 1. And then x naught.
okay, make sure you understand that.
Okay, hold on. I just got confused.
We're just plugging in x naught for x now, right?
Okay.
So x naught, plugging in x naught for n, that becomes that, right?
Yeah.
Okay, now let's think about this one. So we have, this is going to become x naught to the n minus 2 times x naught to the 1.
Oh.
So when you multiply terms, you add exponents. Well, it's n minus 2 plus 1, n minus 1, etc. Same thing. We always have the same amount of x's and x naught in each one of these terms.
Yeah.
Because what are we doing? When we go from here to here, we get rid of one x and add an x naught. Get rid of an x, add an x naught. Get rid of an x, add an x naught. Where to here? Get rid of an x, add an x naught. Gets us to here. How many of these terms do we have?
N amount.
No, we have n minus 1 of them, right? well, we still have one more trick to do, but you think there's n terms here?
Oh, wait. Okay.
How many terms are there here?
N.
Yeah, there's n. Just seeing if I can get you to back out of it. Instead of using what you memorized, actually thinking about it. Yeah, there's n terms here. Because we're going from, if you want to think about counting the exponent of this, we're going from its 0th exponent to its n minus 1 exponent. So instead of counting 1, 2, 3, 4, 5 all the way to n, we're counting 0, 1, 2, 3, 4, 5 all the way to n minus 1.
Right.
It's like 0 through 9 counts 10 numbers. 1 through 10 counts 10, 0 through 9 counts 10. So this one has an x to 0, this one has, or this x naught to the 0, this is x naught to the n minus 1, and everything in between. So does that make sense why this is n times x to the n minus 1?
Yeah.
Okay, boom, we did it.
That is such
Crap, we're not
a-
going to finish these.
Yeah, there's a lot. Oh, there's 2 more pages.
This crap's a lot more.
Or 3 more.
This is more easy to see.
2 more.
Yeah, all these proofs are easy, it's just going to take time. Let's see, what's the next thing it wants me to prove?
This makes you realize how cool calculus really is.
Yeah. Especially when you start
Oh.
looking at
That's going to take some
certain
time.
derivatives of certain functions.
Okay, I guess we'll pick it up from there next time. We'll prove that a differentiable function is a continuous function, because that one might be a little bit, I thought we were just going to keep doing derivatives, because those are easy to just calculate.
So should we do any homework or what?
I would start with the homework if I were you. I would also try doing the proofs that they do.